Okay, now do my voice coming to you? Can you hear me? I hope. If you can hear me, please write. Okay, I think my voice is coming. Uh, I'm sorry because I have some trouble with internet. So the stream has started late, a bit late, uh, nearly 20 minutes. So I'm sorry about the situation. Okay, I think we can start with the problem A. Let me change this. Some, I think the uh, internet problem is still continue, but let me try something. Uh, okay, I think it's now better. The internet is now better. Uh, I'm continuing with problem A. Okay, now in the problem, it says there are n lamps numbered from 1 to n, which are until turned off. We can perform following operation n number of times. We can choose two non-adjacent lamps that are currently turned off, and we can turn both of them. We need to uh, reach the configuration as S equal to 1 means ith lamp is turned on and otherwise it's turned off. Uh, and it says now here it gives the definition of adjacent. Okay, what can we do in this problem? We need to see, we need to make an observation like, let me open this. Okay, uh, if we have odd number of ones, I mean if there are 3 ones, 5 ones, 7 ones, and so on, we cannot make we cannot reach to the configuration because we can in operation we can choose two non-adjacent turned off lamps and we are turning them on. So we are in each operation we are uh, turning on exactly two lamps. So in the end, we will, if we make k operations, we will exactly turn on 2k lamps. So this number will always be even, and therefore, if there are odd number of ones, we can be sure that we cannot make the configuration. We cannot reach to the configuration. So we can output no directly. But if we have even number of ones, can we make all of them? Can we make all the configurations? Let's look on this. If there are uh, there are more than two ones, like four ones, make the pairs like this. Let's say one indexed. We can pair uh, one 1 and 1 2, 1 3, sorry. We can pair 1 2 and 1 4, and so on. Pair all this. We can pair all these ones like in a way so that we can be sure that no two adjacent one will be paired if we have more than two ones. But if we have two ones, we are not sure that we can pair them off or not. So in that case, we can look if, as I said before, if there are more than two ones, we can output yes. Otherwise, we need to look if the two ones are neighbor or not. If two ones are neighbor, then the output will be no. Otherwise, the output will be yes, because there will be some zeros between the ones. So we can pair up these two ones, so the output will be yes. So let's look on the code. Here I'm counting the number of ones, and I'm finding the two ones, the indexes of the two ones, and I'm saying if there are odd number of ones, or the two ones, if there's two ones and one of them is one of them is one index before of exactly one index before of the other one, we should output no. Otherwise, we should output yes. Here, I didn't write if n equal to 2, this variable equal to 2, because I'm finding it like if st is equal to minus 1, I'm making st equals to I. Otherwise, I'm making nd equals to I. So if there are more than ones, if there are more than two ones, like 4 ones, first will be st will be this, let's say 0, and nd will be 0 1 2 3. So if this equation holds, we can be sure that there are exactly two neighbors. So we should output no. Are there any questions? If you have any, you can ask me. Otherwise, I will continue with the problem B. Do you have any questions? Should I continue with the problem B? Okay. So I'm continuing with B. Let's first read the question, read the problem. There are n cows in the tournament. They have rating. Each of the ith one is AI, and it's all distinct. They are all distinct. And the cow is initially in the position E. The tournament consists of n-1 matches as follows. The first match is between the cow in position 1 and the cow in position 2. And the ith match will be in the ith plus 1, and the winner of the match I minus 1. So it will be the maximum in. Okay, let's read this sentence too. In each cow's rating, wins and proceeds to the next match. So we can say that winner of the I minus 1 match will be the maximum of the first I-1 numbers, because it says that the cow with the greater rating will win the match. So maximum number will always proceed to the next match. So we can say that this sentence will equal to the maximum of the first I-1 element. You are the owner of the cow key. If you winning the tournament is not important. The only thing you consider is to win as many matches as possible. You can ask, you can change your index with any other cow, but you can make this operation exactly one times, only exactly one times. But you can choose to stay in your place too. You must not. You can change your place. You can change your index, or you cannot change your. You are not required to change. It is optional. I mean, okay. It says find the maximum number that you can maximum number of matches that you can win. Okay, let's look at the problem. We can say that we can choose to not move. We can choose to stay our current place. When we choose it, we will win exactly. Okay, let's say if we have a number that is greater than us, that I mean, if our rating is say 7, and we have a element with rating with greater than us in our left, let's say 10, the 10 will come, the 10 or greater than a 10 number will come to this match, because we said remains, continues to win the matches. So at least 10 will come to here. If we know 10 is here, then we know at least 10 will come to here and match with 7. So 7 will lose the game, and we will win 0 matches. We don't want this situation. So if we have a number that is greater than us in our left, we should swap our indexes, our places. Because if we do not change our places, we will win exactly 0 matches. Because this 10, at least this 10 will come to here and match with us. So we will lose the game and we will win 0 matches. Also, let's say we have two numbers that are greater than us in our left. We should swap with the leftmost one, because if we swap our 7 with this 10, we still have a number that is greater than us in our left. Let's say we have swapped this and this, 7 and 10. Still we have a number that is greater than us in our left. So at least this 8 will come from here and match with us and win against us. So we will still have 0 wins. So we should swap our element with the leftmost element that is greater than us. And after that swap, we can look to the situation. We can look to the case. That's how many matches can we win. Also, there is this is the first option. And in this option, if we have element that is greater than us in our left, we should swap with the leftmost one. Let's say 7 and let's say 8. Now we know that this, let's say this place to I, we know that I is greater than us. I element is greater than us. Greater than us. But there can be a number that is in the left of the I and can greater than us too, like this 10. So what is the index of this number? It is the second leftmost element that is greater than us. That is greater than us. Greater than us. So we should look to the minimum of their indexes from this and this, minimum of the second leftmost element and the I, because we know that when we swap I with the leftmost element that is greater than us, we know that now I is greater than us, and the second leftmost element is also greater than us. So we can look to the minimum of them, and we can win the matches option. And the second option is to swap this swap the current number with the first element. When we swap our current element with the first element, it can win more matches, because we know that we have not any number that are greater than us in our left. So if we put this element, if we put our cow to more left, to the left more, we can win more matches. So we can swap our cow with the first cow and look to the answer. Let's continue on the code, and I think you will understand more in the code. Firstly, I'm finding the leftmost element that is greater than us, our cow, and the second leftmost element in our left, which is greater than us, and I'm finding them with iterating, and if AI greater than AK, and 1 is equal to n plus 1, I'm saying 1 is equal to I. Otherwise, if AI is greater than AK and 2 equals to n plus 1, I'm saying 2 is equal to I. And with this method, I'm finding the leftmost two leftmost cows that have greater rating than our cow. So by this way we have found the 1 and 2 variables. Okay, then firstly I am swapping my cow with the first cow. So when we swap our cow with the first cow, what will be our answer? It will be 1 minus 2, because 1 is the leftmost cow that is greater than me. And when I am in the first position, the matches that I will win will be 1 minus 2, because there are exactly 1 minus 1 matches from 1 to 1, and we will lose the last match, so we can only win 1 minus 2 match. And here I'm the I'm finding the second option, uh, which we which we said which we thought first in the problem while thinking. In this uh, in this option, we are swapping our current cow with the first with the leftmost cow that's greater than us. So I'm saying that if k is greater than 1, so our cow is now in the right of the first cow that is greater than us. And if there is a cow that is greater than us in the array, I'm saying that this variable equals to minimum of k, comma 2, because what we said before, the cow in the k position will be greater than us because we swapped the 1 and the k positions cows. Also, the cow in the 2 is also greater than us because it's the second leftmost element that is greater than us. So we should find their minimum, the minimum index. After that, we can say answer is equal to maximum of the answer and the this variable minus 1 minus 1 equal to 1, I said, because this is because we are in the 1 position and we will find the position in the this is the position last position that this is the first position that we will lose a match, and this variable is our current this variable is our current position. So this equation will be our answer when we swap the cow in the 1th index and the kth index. So when we maximize these answers, we can output it and we will solve the problem. Are there any questions about the problem B? If you have any questions, please feel free to ask it in the chat. I'm waiting your response and I will continue if you don't have any. I will continue with the problem. Okay. Let me wait a little bit too. And if there will not be any questions, I will continue. Okay, I think there is no questions. There are no questions. There are no questions. So I will continue with problem C. Okay, what it says, let's read. You want to reward each of your K employees, so you should buy a ticket for all of them. You have N days, and price of the ticket in the ith day will be AI. However, there are some rules. You can buy at most M tickets in a day. So you cannot buy more than M tickets in one day. And if you purchase X tickets on day I, all of the subsequent days from I plus 1 to N, their price will increase by X. It's as it says, let's say the array is first here. The first array is here, and you have purchased 2 tickets on day 1, so it costs 2 because 2 multiplied by 1 is equal to 2. You have bought 2 tickets, so the total cost will be 2. And from the day 2 to day 2, 3, 4, 5, day 5, the costs will be 5, 10, 6, and 7 because we have purchased 2 tickets. So 3 plus 2 will be 5, 8 plus 2 will be 10, 4 plus 2 will be 6, and 5 plus 2 will be 7. And it says if you purchase 3 more tickets on day 2, they will cost for 15 because 5 multiplied by 3 is equal to 15. And the price from day 3 to day 3, 4, 5, 5 will be 13, 9, and 10 because 10 plus 2, 3 is equal to 13. 6 plus 3 equal to 9, and 7 plus 10, 3 equals to 10. We should buy K tickets, exact K tickets, and we should spend minimum amount. Okay. Let me open. Now, what we can do? Let's think about it. We can firstly think that if we want to buy in the ith and ith plus 1 days, if we want to buy some tickets in I and tickets in some I, or not say I plus 1, say like J. If we want to buy tickets in both I and J, let's look on the situation. Let's say we have bought X number of tickets here. So all the numbers in here will increase exactly X. So if we buy a ticket in here, the cost of buying from J or K will not change because they will both increase by X. So if J is smaller than K before this operation, before adding X, J will still be less than K after adding X because we are adding the same amount to the all numbers after here. So if we buy the I ticket, the order of their amounts, the order of the sorted order of these elements will not change because we are adding the same amount to all of them. So before choosing I, if choosing J is better than choosing K, after choosing J is still be better after choosing E than K. And if choosing J is not better than choosing K, after choosing E, J cannot be better than K because we have added the same amount, so K will still be better than J. So after making this observation, we can say that the order that the elements that we will choose will not be affected from the elements that we have chosen. So choosing 1, if we said we will choose 3, we will purchase tickets on day 3, if we buy some tickets in day 1, it's we will still continue to we will still buy we will still purchase a ticket on day 3. Either if we choose if we buy tickets, if we purchase some tickets on day 1 or not to buy in day 1, we will still uh, buy tickets and on day 3. So choosing tickets on some day is not affected uh, in from anything from the tickets that we have bought in the previous operations. So we can say that if nothing is uh, affected by the chosen tickets, chosen days, so we can say that the problem changed to the problem that choose some tickets for in some days that and the total the tickets that you have chosen will should equal to k, and in each day you can choose at most m tickets. The problem is changing to converted to this problem. So uh, let's say okay, this sentence isn't will not affect our solution, will not affect our answer. It will only affect the output, but it will not affect our strategy. Our strategy will be same if we erase this sentence or not. We will use the same strategy. We can use the same strategy because of our observations. So, how can we solve the problem when this sentence is not hold, not exist? We can choose the minimum numbers so that we can find the minimum answer. I mean, we can first select two tickets from here. We can select all the tickets that we can buy from here, so that we can buy two tickets from the fourth position. Let's say 1, 2, 3, 4. We have about 0, 0, 0, and 0 tickets. After we can say that this is the smallest element, so we can buy two tickets from here. After that, the smallest element after this element is this element. We should buy tickets from here. So we can buy one ticket so that we have bought three tickets because k is equal to 3. So we should buy exactly 3 tickets. So we can buy like this. Now let's consider the answer. 8, 6, 4, 2. We have bought one ticket from here. 4 plus this cost has increased and it become 3, and we bought two tickets. So 3 multiplied by 2 equal to 4 plus 6 equal to 10. And the answer is 10. Now let's continue with the second example. Okay. Let me write again. 1, 2, 3, 4. We have about 0, 0, 0, and 0 tickets. Firstly, we need to buy 8 tickets, so we must buy 2 tickets from each. So that answer will be 64. This is not a good example, I think. And in this example, we will only choose this ticket, so the answer will be 1. and in this example, it nothing is important. Choose any three of these stakes so that and the two. It is not important that choosing these three ones or this and this and this or any other option. They are all same. I think the best input in this task in the sample is this for understanding the solution. And let's continue with the code. Firstly, I have read three inputs and N, M, and K. After that, I have inserted all the elements with their indexes to a set because I want to find the minimum indexes so that I can choose that day to buy tickets. Because choosing the minimum day, the minimum cost day, is better, as we see, so that I am inserting all elements to a set that I can find how many tickets should I buy in which day. I will find with this set. After that, I am iterating in the set so that I am iterating from smallest element to the biggest element. And by this way, this is what I want. This is the thing I want because I want to iterate. I want to first buy the smallest ticket, then the second smallest tickets, and so on. And I'm saying that I have a variable like this. If it is this variable plus m is greater than k, I can only buy k minus this variable in the day. So I'm saying that the tickets that I have bought visits array means that visit e means that the tickets that I have bought, the number of tickets that I have bought in the ith day. So I'm saying that visit this element. This is seconds are in the set gives the index of elements in the array. So I'm saying that this equals to the number of tickets in this day equals to k minus this variable because only this much tickets remained that I need to buy. Otherwise, I'm saying that I will buy m tickets in this day because I can buy at most m tickets. And I'm adding m to this variable, and if this variable is greater than or equal to k, I have completed to buy the required number of tickets. So I'm using break to stop this loop. After that, I'm using this account that holds for how many tickets that I have bought in the previous days. So I'm adding this to the answer because this is equals to the number of tickets that I have bought in the ith day, and I'm multiplying it by AI plus count. AI is equal to the value of the tickets in the ith day, and I'm adding CNT because this says the number of tickets that I have bought in the previous days. So the cost of a ticket in the ith day has increased by CNT. So I am adding them up and multiplying by with I so that I am finding the cost of buying tickets in the day I. After that, I'm increasing the count by with I because I have bought exactly with I tickets in the I day. And then I am outputting the answer. This is the solution for problem C. Are there any questions on this problem? If you have any, you can ask me. By this way, we have solved in n log n time complexity of this problem. In this There's a question like this. I initially submit my code and got a wrong answer on pretest 2, but then I changed some of my int to long and it worked. My question is, should we take all the variables to long for no risk? I'm using like something like define int to long so that I'm using all variables as long. This has some drawbacks because long is taking more memory in the system because if I'm not wrong, one integer is equals to 4 bytes and one long is equal to 16 bytes, as I know, but I'm not sure. Maybe it can be 8, but it can be 8. But however, it is more than int, so it takes more memory in the problems in the system, and also summing up or doing something else in integer is more faster than long because let's say one an integer is 4 bytes means 32 bits, like let's say 1100000001 and so on, goes like this. There are 32 numbers, and let's say this is number a equals to this, and let's say b is equal to something like, it is not important, and when you sum up, you are summing up 32 bits, or when you multiply, you are multiplying 32 bits, or when you make any operation, make any if, else, or, XOR, and so on, making to this operation to 32 bits. But when you use long, you are making all these operations to 64 bits. So it is also takes more time. When you use long, it is working a bit slower than using when you use ints. But there is only very small differences between using int and long in both memory and time in the practical manner. So in Codeforces and some runs like this together and so on, when you submit a wrong answer, you are getting a huge penalty in the contest, like minus 50 or plus 10 minutes. These can be very huge penalties for a participant. So using long is better to be sure that you have not any bug because of this intent long issue. In some problems, I remember that I was take time limit or memory limit because of this long issue, but it is very rare that I took these errors. Generally, it works with no problem. Yes, as you say, it can take uh, many minutes, so I'm using define int long to guarantee that to not leave some problem like this. Okay, I think, okay, I think it's 8 bytes because there's a command like 8 bytes. 8 bytes is more sense because integer is 30, one integer is 32 bits, and it is 1 bit, 8 bit. So 8 bit equal to 1 byte. So this is equal to 4 bytes. Long is equal to 64 bits. So it will be 8 bytes. So 8 bytes is more sense. Okay, let's continue with problem D. Okay, Alice says N coins, and Bob says Bob have a jewelry store. Uh, Alice will buy exactly K jewels. Uh, Bob have 60 stalls, uh, each of it amount of jewels, and he has not set the prices yet, but he can set from 1 to 10 by 10 powered by 80. So Alice buys greedily. Uh, so she goes to stall 1 and buy as many jewels as possible. It means the many number of jewels that she can buy. Uh, she's buying the as many possible as many jewels as possible as she can buy. Then she's going to stall 2, buy as many jewels as possible, and she's continuing to until to the last stall when he when she reached to the last stall and buy some jewelries from there. She is stopping. Uh, Bob Bob knows this strategy, the strategy of Alice, the greed strategy of Alice, and he wants to set the prices so that Alice can buy exactly K jewels. Uh, so we are in this problem. We are helping to Bob so that if it is possible, we should output the number of stalls and price of each stall. And if it is impossible, we should output no. Like if uh, Alice wants to buy 3, uh, sorry, if Alice wants to buy, yes, 3 jewelries, and if she has 7 money, 7 coins, we can make something like, so we can put the stalls like 10 stalls, 2, 3, 4, 5, 6, 7, 8, and it goes up to 11. When we set up the first cost by 2, it will be she will buy exactly 3 jewelries, because first she has 7 coins, then she will buy 1, then she's coin will be 5, then she will buy, and she's coin will be 3, and she will buy 1, and her coin will be 1, and by this way she have bought exactly 3 jewelries, and after that she cannot buy any jewelries with 1 coin, so she has bought exactly k coins equal to 3. And if she cannot make this, she cannot bought k tickets, jewelries, we should output no, like 6 and 4. We cannot buy 4 jewelries with 6 coin. Okay, what can we do in the problem? Firstly, if I think looking on the code is better than this problem, on this problem. This problem is some case that we need to consider. If k is equal to n, we can have 1 stall, and the cost of the jewelries in that stall can be 1, so that we can buy exactly n tickets and jewelries, so that n is equal to k, so we have bought exactly k jewelries. So if n is equal to k, we can output 1 and 1. Yes, 1, 1. Otherwise, if we can output like this, this is the option that if the answer is yes, we can put to the stalls. And let's write like here, like this. First, we are putting n minus k minus 1, and after that we are putting all ones. This is because we are putting exactly k minus 1. We are putting n minus k minus 1, so that we are buying. We should buy, as I say. I'm not saying we are buying, because in the no case we are buying more than 1. So in this case we can set the prices so that in the first stop we should buy exactly 1 jewelry, and our cost should be k minus 1. And when setting up the price like n minus k minus 1, we should buy 1 jewel, and our cost should be k minus 1. So that when we output 1, we can take exactly k minus 1 jewelries. So that we can buy 1 jewel here and k minus 1 jewelries here, so that we can take exactly k jewelries. The no case comes from here. If this k minus 1 with putting n minus k minus 1, if we can buy 2 jewelries with this cost, then our more jewelries here, then our cost will not be k minus 1. So our cost will be smaller. And we don't want to have a jewelries that is smaller than k minus 1. We don't want to have a coin that are smaller than k minus 1, because if we have less than k minus 1, we cannot uh, reach k by putting 1 or something else, because we should bring the maximum number of jewelries that we can buy. And if we put whatever we have put, we cannot buy exactly k jewelries, so the answer should be no. And it is the case that k multiplied by 2 minus 2, because it comes from k multiplied by 2, it is like 2 multiplied by k minus 1 equals to 2k minus 2. So that 2k minus 2, if 2k minus 2 is greater than or equal to n, output should be yes, and 2 stalls, n minus k minus 1, and 1. This is the solution of the problem D. Are there any questions? If you don't have any, I will continue with problem A. But if you any, I can look to it. Okay. Can you explain the 2k minus 2 condition again? Say that if n is not greater than, let's say, let me give an example so that it can be more clear. Let k equal to 3 and 2, 4. Okay. And let n be 4. Now, what did we set? We can put like n minus k minus 1. After that, we can put 1. But let's use this strategy in this input. Firstly, put k minus 1, n minus k minus 1. It will be 2. After, put 1. When you put 2, n is equal to 4. So we will buy 2 jewelries. And here, our costs will be 0. So we cannot buy any jewelries. So we will buy totally 2 jewelries. So we cannot buy 3 jewelries. So we cannot reach our condition. We cannot satisfy our condition. So the things that we don't want, this happened. This is because we should buy exactly 1 jewel in the first operation and k minus 1 jewelries in the second operation, in the second stall. So n minus k minus 1 should be 2 multiplied by this should be less than n. So putting this k, if we put something like this, its output will be no. How does n minus k plus 1 give exactly? Let's look on the example to it. Uh, say 4 7 minus 7 minus 3 minus 1 equal to 7 minus 2 equal to 5. And when you put 5 on the first stop and 1 on the second stop, you will buy 1 joule in the first stop and cost will be 2, and you will buy 2 jewelries in the second stop, so that here you have about 1 and here you have about 2. In the total you have about 3 jewelries. Do you understand? Any questions? How do we know that there is no strategy other than n minus? Can you explain why Bob can erase at most? I don't know why there's 60 stalls limit. Uh, I don't know, are there any other methods? Maybe the solution of the editorial is something else, and after the editorial has published, you can look to the solution of the author. Maybe he used this 60 limits. Okay, why this is sufficient? Let's think on it. Maybe it is only, by the way, a trick to if they write 2 to here, everybody can solve it. So they're writing 60 so that it should be harder to find the solution. Why and outputting n minus k minus 1 and 1 is optimal, and there is no solution other than it, if it is necessary and sufficient condition. Think like putting anything else to the output. I don't have any certain proof, but uh, say that if n divided by k is greater than 1, you can use exactly n divided by k, because it will give a result greater than 1. So you can use n divided by k, so that n divided by k will equal to k. And otherwise, we can look to this case, and sorry, not this case, to the case that n divided by k equal to 1. Let me do it here. Okay. When this condition holds, n divided by k is equal to 1, so our strategies have is limited because we cannot put anything that we want. So in this case, we should, what we know, k is too big because if k can be small and divided by k can be greater than 1. So in this case, we know that k is big enough. K is greater than n divided by 2. So in this case, uh, we should decrease n a bit, but if we decrease a lot, we cannot take exactly k amount. Let's say if you said 2 in here, if you use 2 as in a one stall, you need to have 2k 2k jewelry, 2k coins, exact at least. So if you use 2k is greater than n, we know it, so that we cannot use 2. So we should use 1 in some place. So if we use 1 in some place, in some case, we can know that we should buy some x jewelries, and after that operation, our cost should be n minus x, so that we should output 1, and we can buy n minus x jewelries. So in the total, n minus x plus x jewelries equal to n, and 1 and 1. We cannot put anything with 1. And if we cannot put anything with 1, uh, we cannot make this input. We cannot buy exactly k jewelries because we know that we must buy 1 in this case. If we not buy 1, we should buy minimum 2, and 2k is greater than n. So we should buy some time, and this is the best option for buying 1. Any questions? Now do you understand the reason to it? Okay. Okay. Let's continue with problem A. I will not show the solution code for this. I will only tell the reason of the solution, tell the solution. Okay, we have a string with lowercase Latin characters. We need to partition it to substrings. Each substring will not be a palindrome. Like this is not a palindrome. We can output it. This is a palindrome, so we can partition it like UW, UOW, UOUWU. So we can say that each of these 3 strings are not palindrome, so it's okay. It's not possible to partition this as not palindrome substrings. Okay. If the string in this problem, if the string is contains this, otherwise, if the length of the string is even, like this, let me look 2, 3, 4, 5, 6, 7, 8, 9. Not like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, but in this is not a good example. If a string is not palindrome, we can output it directly like this. If a string is not palindrome, we can output it directly. If a string is palindrome and its length is equal to if its length is equal to an even number, we can partition it from the middle. Let's say ABB. Also, like it is the edge case, but let's say ABB, ABC, CBA, ABC, CBA. Partition it from the middle, and we can decrease one of the decrease this uh, array, decrease one index left, so that this will be palindrome and this will be not a palindrome and this will be not a palindrome. This part will not be a palindrome. This part will not be a palindrome. Otherwise, if the length is odd of if this palindrome, we can find the odd palindrome, smaller odd palindrome, and we can partition it from there. Let's say, okay, let's say like here. Then decrease it by 1, and then partition the remaining part. Remaining part by the thing, or find a odd length, not palindrome string, not this part. Let's say 3 or 5, like this, and after that the remaining part will be even. And if it is not a palindrome, we can output it, and if it is a palindrome, we can divide it by half and use the same technique that we have mentioned, so that you can solve the problem. I think this is the solution of the problem E. I'm not sure about this solution, by the way, because I've not written the code for it, so I'm not sure. But I think it is sensible solution. If it is all even palindrome, divide it by half and decrease one index before, and let's say middle minus one element, middle plus one element. And if it is odd, find an odd non-palindrome string and solve the other part by itself. Okay. Now I will finish the stream here. Are there any questions? If you have any questions, feel free to ask before I stop the stream, or otherwise I will stop the stream. I am waiting questions of you, and if you do not have any, I will stop the stream. You can ask whatever you want. I think, but I will wait until 15, and if no question will come, I will stop. Okay, I think no question will come. Thank you for watching me. I hope you have understood the solutions and this video, this stream was useful to you, useful for you. Thanks again for watching. Goodbye.